Please proceed to the next slide. So when we look at the primary data pathway in any mobile network, we would see that there are different core blocks that come in the pathway. Of course, everybody understands protocol stacks. I hope that in this audience, everybody is aware of such things, protocol stacks. So in case of mobile, the stack looks somewhat like this as per the slide. You have the core network, which is sort of the backend, where you have connections to the IP layer and the core internet as well, apart from the telephony network. Right after that, you have the very first topmost layer in the stack, which is composed of two subunits, RRC and PDCP. RRC stands for Radio Resource Control, and PDCP is another layer which is related to packet data convergence protocol. So these two are integral to handle the data at the packet level, and also to make decisions on, say, semi-decisions on routing and things like that. If you look at the core standard, which is relevant for all the mobile data pathways, it is the 3GPP standard. Among them, basically, there have been multiple releases over the last 2 decades. The most prominent recent release is release 16. In fact, release 16 stage 2, which came this year, June. So in this particular standard, if you would like to know more about RRC and PDCP, the specific numbers or the standard subsections where it is detailed are in 36 and 38 sections, primarily in 300, 331 and 323 series. So the job of this RRC and PDCP is about making decisions and also maintaining quality of service at the packet level. Whereas if you go to one level lower, you have the radio link control as well as medium access control bundled as one layer, which is responsible for preparing and sort of aggregating packets for different users and for different, I would say, functions together, and then patch it to the next layer down, which is the physical layer. So the PHY layer or the physical layer is all about bit level handling. Till MAC layer, it is sort of like at a frame level or a packet level handling, whereas when you come down to PHY layer, as in any other networking stack, you are dealing with raw bits, direct bits. So PHY layer is all about bit level processing, both in terms of preparing it or sending on the actual analog pathways of RF and on the channel, as well as once you receive the data back from RF, being able to correct, estimate, and then remove all the channel related problems, and then get back the data and packetize it and give it at the frame level to the MAC. So that is the core functionality of the PHY layer. There are many smaller parts in the PHY layer, which I will slowly come to later. And the last section here is the RF section. The RF section is the analog section, which is all about handling the signal as voltage or a voltage swing coming at periodic intervals from the PHY layer, and passing it on to the antenna, which is also part of sort of the RF box, and radiating it over the channel. If you look at the tower, which comes in 5G or all the way from 2G to 5G, all of them have similar base level blocks. However, the complexity in each of them has changed and increased over the different standards, primarily to support more capacity. Let's go further to the next slide. So if you look at the evolution of the mobile standards, all the way from 2G to 5G, I have just removed the 2G part from the discussion to simplify the matter, as that is quite out of date and it is not in use much. If you look at the 3G standard, which is still being used in India, the frequency bands are ranging all the way from close to about 700, 800, 900 megahertz, all the way to something like 2.1, even in some cases 2.4 and 2.6 gigahertz. So those are all the different bands in which the different service providers send their signals and our mobiles receive and transmit. But the bandwidth, which is basically the core distinction of how much can you really utilize the resource of the band, that is of the order of 5 megahertz to 20 megahertz in case of 3G. Using this, if you were to pack in a lot of bits, as you would be aware of the different modulation techniques, like the QAM modulation or the QPSK modulation. If you consider 3G standard had up to QAM 64, which would put the max raw data rate at the level of 120 Mbps. Remember that this is the data rate at utilization of full 20 megahertz channel slot, which is like one entire cell size capacity. So this capacity is not actually what comes to your mobile. This is the capacity that the cell site can give to all the users who are connected to that particular cell. The latency figures that were there were of the order of 100 milliseconds, and in worst case scenario going up to 0.5 seconds as well, which is a very large delay. And the cell size or the size of each cell used to be quite big. You had 1 kilometer all the way to sometimes even 10 kilometers. The nominal used to be about 1 to 2 kilometers. Whereas if you go to the 4G LTE or the LTE advanced standards, which are currently in use, and most probably all your mobiles that you are currently using are using these bands, they have stretched the phase band a bit, even gone to about 3 gigahertz plus band up to 4 gigahertz, and the bandwidth was increased from 20 megahertz on the higher side going up to even 90 megahertz. But that doesn't mean that in a particular cell site it is being used. That depends on the option as well as the operator's capacity there, what he has deployed. Typically, it will be of the order of 20 megahertz to 40 megahertz. But with that, the additional step that they did was the modulation techniques. They said that they can support even higher. So they changed the modulation techniques to go up to QAM 256, which is like packing 8 bits per hertz, which translates to about 720 Mbps or 90 megahertz. So that was a major change. And the latency was brought down by simplifying certain network elements, and the cell size shrunk. So this is an important thing to remember. Across the generation, you would see that the cell size, the size of each particular RF cell decreased continually. The primary reason for this is that for a given capacity, which gets defined by the bandwidth, you would want to support higher capacity per user, and that can be attained if you shrink the cell size more and more. So that is where the cell size is an important aspect of the generations that as and when they changed. So another important thing to remember, the definition of a cell in mobile terminology is a unit where you have an RF or a radio unit. So that is a core definition. So basically what it means in case of 5G is that you could have radiating units as close as 100 meters to each other. So let's go further. Sorry, I missed one other aspect. Can you go back? In case of 5G, one important change happened for the frequency band. Over, I would say, close to 8-9 years of exploration, people came up with two distinct frequency bands. One band going up to 7 gigahertz, which is composed of several smaller sections, all the way from 400, 450 megahertz to almost like 7.125 gigahertz. Different slots were identified for different possibilities. So these were identified with the objective that these could be used on your mobile. Whereas there was one second type of frequency band that was also identified, which is called as FR2, which is ranging from 24 gigahertz to 40 gigahertz. Now, this particular frequency range is an important one in terms of higher and higher capacity. So if we look at the bandwidth, I think I have not written it here, but I will orally say, in case of FR1, the bandwidth goes up to 100 megahertz, whereas FR2, the bandwidth can go up to 400 megahertz, which is a primary advantage as you go to higher and higher frequency. The core bandwidth that comes to your hand is much, much higher. But is that all? Is that the only thing, and there is no catch? It's not like that. When you go to higher frequency bands, we have to always remember that the wavelengths become shorter and shorter. When the wavelengths become shorter and shorter, the traveling waves become more and more directional. They do not bend easily. So that introduces a certain problem if you want to access these kinds of frequency bands from a cell tower and you being inside, let's say, a building, or you being not in the direct line of sight from the tower. So it poses certain problems of that kind. So FR2 on a preferential note is going to be used between towers to tower more and less to go to a particular mobile device. It could be potentially used also for, let's say, vehicular purposes. That is a possibility, but very less likely to reach on a mass scale to mobile directly. So the bandwidth, just go back, please. So as an understanding from all of this, you see that the max data rate for FR1 band has gone to something like 800 megahertz, 800 Mbps, which is similar to the 4G LTE advanced, which could go till 720. It seems like, okay, nothing much changed, but that is not the reality. In case of 4G, the 90 megahertz slot is a very rare case. The more common cases are something like 20 and 40 megahertz, whereas in case of 5G, the higher bandwidth slots are more likely. So the FR1 is likely to reach closer to 800 Mbps. If not exactly that, maybe it will come down to something like 500, 600 Mbps. Whereas FR2 is the additional important change where it can go to several Gbps. Apart from that, the definitions of various stack components were improved so that the latency could be brought down to 1 to 10 milliseconds. So these are the primary changes at gross level that we can notice in 5G as compared to the previous standards. Let's go further. So at a core level, the objective of 5G is essentially to support large data rates, something like 50 to 100 Mbps per user. Remember, all the capacities that were mentioned in the previous slide was all related to cell site capacity, not per user capacity. So here I'm mentioning the per user capacity to go higher. In case of 4G, it was, I think, going up to about 20 Mbps. And on a nominal note, it used to be something like 4 to 5 Mbps. And also to support low latency applications, So this is an important, I would say, thrust in the 5G to support and diversify applications to not just be limited to mobile telephony, but also for industrial and automotive applications. It's a big boost that was introduced in terms of 5G specifications and also the changes. Another important evolution, I would say, of 5G is that unlike the previous generations, where the topologies were limited as options, in 5G the topologies are very diverse. So you could potentially adapt it for different use cases, whether it's an urban dense tower requirement, or a rural where you need a sparse tower requirement, or an enterprise where you need a very large capacity throughput in a concentrated way. So those kinds of use cases could be supported. So such heterogeneous network architectures are possible with 5G. Let's go further. So now we'll just analyze. We had such a clear setting of 5G where we want ultimately more data per user, and we would like to have less latency also. So what does it mean, or how can such an objective be achieved? So more data can be achieved in three possibilities, or in three ways per user. So the first one is introduction of the new technology, massive MIMO. If you are aware of, in the 4G scenario, also there were MIMO antennas. In fact, most likely all of your phones already has a 2x2 MIMO antenna. But here we are talking about a bigger array, going up to like 4x4, perhaps on a mobile telephony, and at tower level going up to 8x8 MIMO antenna. Now, that essentially helps in achieving better spectral efficiency. In all the previous mention, I was talking about QAM 256. Even though that's a nice thing to have, it's not so easy to achieve. If your channel is just a simplistic one antenna to one antenna, or a few antenna to few antenna to few antenna, you need a larger channel, or a more diverse channel to support such higher capacities, especially in varying environments. So that is where massive MIMO comes into play. So it gives better spectral efficiency. So if you say QAM 256 in 4G, whether that was achievable versus whether it is achievable in 5G, the possibility of it happening in 5G on a more regular basis is higher with massive MIMO. Another important dimension of massive MIMO is that it's a fully digital array. So all the array elements, feeds comes directly from the digital domain. So that enables one other possibility, which is multi-user beamforming. So you could potentially have some kind of shaped higher power beam going in a specific direction with a beamformed wave, which is directed for a particular user while you are also serving other users. And you could use that to enhance cases where you see more packet drops. So that's an important possibility with massive MIMO. So that is another thing which will improve basically the data throughput. But this comes with a certain catch, which is the cost of the core technology will be higher, and the base unit both on the mobile telephony as well as on the tower side, and the overall complexity of the system is higher. Well, complexity is obviously increasing with every generation. So this would be another increment on that complexity, but a very important thing. So the complexity as a disadvantage is likely to sort of be overruled by the positives that this massive MIMO technology brings into play. So this is one critical dimension which will help in improving or increasing the capacity per user. Another important aspect is to use larger and larger bandwidth. Larger bandwidth directly translates to the fact that you need to have that much bandwidth available as a spectrum slot. At lower frequency bands, the availability of such bandwidth is lesser and lesser, unless other services, let's say the already allocated 2G, 3G, 4G kind of bands are relinquished and reused for 5G, and the government comes up with better policies for it. And the other possibility of increasing the bandwidth is to go to even higher frequencies, which is the FR2 band. The FR2 band brings in even more capacity, very large bandwidth, and that will directly translate to the capacity that you can deliver to an end user. So this is the second most important aspect of it, but that comes with a catch. When you go to 24 to 40 gigahertz, which is sort of millimeter wave bands, you have lesser bending ability of the wave. So if you are inside a urban setting where you have buildings and you have the towers, if you move from one room to another room, you could potentially have a disruption in the signal in case of higher frequencies, more strongly than what you see in the lower frequency band. So this would require more infrastructure-oriented approach where you install something as a fixed unit pointing to the base station, and from there you say connect to your phone via other technologies, maybe Wi-Fi, or using the lower bands of the 4G. So that would be a necessity for it to be more practical to realize for urban indoor kind of setting. The third most important dimension of getting more data is to reduce the cell size itself, which is something which is being done in case for every generation from 2G to 3G to 4G to 5G. The cell sizes are continually shrinking, and 5G is likely to have cell sizes going up to even maybe 50 meters to 100 meters. That would mean that in each cell site, the number of users that the cell has to serve is lesser and lesser, which means that the capacity per user will naturally go higher. This obviously translates to higher cost, which is an important aspect to solve in the 5G. And obviously, they have good solutions, which I will talk about in the future slides. Let's go further. So in the previous slide, we talked about how to increase, or rather how 5G is set to increase the capacity per user. Now let's talk about the lower latency part. Lower latency can be obtained by three means. One is that you upgrade your architecture and processing elements, hardware elements, to be capable of processing the stack very fast. And 5G as a standard has simplified certain elements in the stack, which will make that possible. Second is that given that the cell sites are smaller, so the ping, or rather the first hop reaching ability is much sooner, and the rest of the network is usually more deterministic. The last hop from the cell site to the mobile is usually the most indeterminate link. So reduction in pathway for that is going to aid in improving the latency, but that comes with increase in cost, as we discussed in the previous one. The other important aspect is to reduce the number of hops for reaching from the source to destination. So that is another aspect which I will talk about in future slides. So these are the primary things that need to happen for a decrease in latency. Let's go further. So now we go to the more detailed version of the full pipeline. In the very opening slide, I had given you a very simplified top level split, where from the core network, you had the RRC and PDCP as one block, and you had RLC and MAC as another block. which was like a layer 3 and a layer 2, and then you had the 5 layers as one more block and RF. So here in the slide, what you see is a more detailed split of that, with each of the layers having a low and a high, except for the top 2 layers, and each of them being an option as a point where you could potentially do a split. Now, what do I mean by split? So, as we talked about in the previous step, we have to the 5G's primary objective is to reduce the cell size, the size of the cell, which means that the number of cells increase. So you need a more optimal mechanism for realizing the network. So the whole stack or the whole pipeline needs to be split at optimal points so that you could realize the whole network with lowest cost. So that's where I would say a massive discussion, debate happened in the last 3-4 years in the industry. And these were the different option points that everybody identified that, okay, these are the possible splits. But which one is most probable? So that is what is to be discussed further. But in this slide, I would like to highlight some important aspects. If we were to split at option 8, for instance, option 8 is basically the last point, then the capacity, let's say we make that as 2 units. So the RF goes into one box and the rest of the things go into another box. Then the capacity of the line connecting the two will have to be an astronomical number of 307 Gbps. Now, even the fiber infrastructure is not so adequate to support such a high capacity between 2 units. So, for obvious reasons, so that option was basically ruled out. Why is it 307 Gbps? You could compute yourself. RF unit essentially would have, let's say, if you consider a 8x8 MIMO, which is at the tower end, you have basically 64 streams at RF level. Each stream is for 100 megahertz, and let's say we are using a bit packing of 8, which is like COM 256. If you are using COM 256, which means there are 8 bits per second per hertz. So that makes it 800 into 64, and let's say there are 3 sectors per cell site. So you need to do into 3. So if you do all that computation, you will end up with 307.2 as a capacity. So there is something more which gets added, which is that between the low-fi and the RF, the data that is being exchanged is actually complex numbers. It is not just raw bits. So the capacity that each sample of data needs to be given is not just 8 bits. It will go higher. For the sake of this particular calculation, I have used 16 bits for that as a complex number of 8 bits each. So that itself will give you 307.2 Gbps, which is infeasible to realize. So that was clearly ruled out. And then people started evaluating other options. So option 7, where it is 4.8 Gbps, looks more reasonable and somewhat realizable from the point of view of splitting. So why would you want to split? How does it increase say optimality, or how does it make it much better? So it makes it much better because you could put the rest of the sections before option 7 into one box and deploy option 7 onwards, whatever is there, into multiple units and cover, let's say, 3-4 cell sites, and rest of it can be integrated in one box. So that way you are minimizing the complexity of the system which gets finally deployed at the cell level, and you aggregate the rest of the functionality into one box. So that is why this split is an optimal way of simplifying the network requirement and reducing the cost of the network. So option 7 was a possibility. I will talk more in detail in further slides later. But option 6 is another possibility where you have 2.4 Gbps, but that would translate to saying that the entire PHY related bit level processing all will have to be done at the radio unit level. So there are some intermediate cases which standards such as EC3, which I will talk about a bit later, where they split inside the high PHY layer, the higher end of the PHY layer. So that is another possibility, which is in between 6 and 7. So those are certain other options. You have another possibility, which is dealing with mostly at layer 3 level, which is RRC and PDCP, could be again aggregated in a separate box. So that is what sort of came out as a convergence, I would say, as a generally accepted convergence across different companies when they started working towards the split options. Let's go to the next slide. So this is a sort of a general accepted situation that people have come up with all of these different iterations and possibilities. The first two boxes, which is related to layer 3 and communication with the core network. So that section was termed as central unit, and the part in between option 2 to option 7 was called as the distributed unit, and the last section was called as the radio unit. So that is the terminology that has evolved in the last 2 years. Almost, I think there were several articles published even in October 2018 about this particular split. And you can see that this would translate to something like 4.8 Gbps link capacity in between DU and RU, and similar to 2.4 Gbps between CU and DU. So this is an important convergence of an architecture that came about in 5G. Let's go to the next slide. So if you now visualize what was discussed in the previous slide, in a network topology sense, you would see an architecture somewhat like this. You have a central CU unit, which is handling, let's say, a bunch of DU units. In this example, I have taken 3 such units, and each of those DU is handling 3 RU. So this is a kind of topology that is a possibility from the 3 splits, the CU, DU, and RU. And the 3 links which come in this path is the link between RU and DU is called as front haul. This is a new term which is being redefined from what was it defined in case of 4G. So the definition has evolved to the link between RU and DU to be called as front haul, and the link between DU and CU is now called as mid haul, and the link which goes to the core network from CU is called as back haul. If you were to roll back and see how the architecture was in case of, let's say, 3G, all of these used to be aggregated in the final RU section itself, and you would have just one back haul. So that is how the architecture was in case of 3G. And in case of 4G, they did a minor split, I would say. The RU was separated and the DU and CU was still kept together. And then you had front haul and back haul in case of 4G networks. And that was not there in all places, but in places wherever it was useful, they did that kind of deployment. Now, in case of 5G, the split has gone further. You have back haul, mid haul, and front haul with different capacities in each of the links. So just so that you understand these calculations. From the previous slide, I had mentioned about 4.8 Gbps link between RU and DU, and that is coming if you just compute as one channel with COM 256 for 100 megahertz data rate. So if you do that calculation, you would directly end up with 4.8 Gbps. Now, once you aggregate it across RUs, each of the link capacity after DU's processing will come down to 2.4 Gbps and 3 such things. So into 3, hence you get 7.2 Gbps as the mid-haul capacity. And 3 such links aggregated at CU level, and further comes the backhaul, which is the link to the core network. So this is the kind of split. This is for an extreme case. Remember that this is for the 64 massive MIMO being present in every of these RUs, which may or may not be the case in actual deployment. So in actual deployment, there can be different scenarios coming along. And even the bandwidth, I've taken 100 megahertz, which is for FR1. FR2 case would change the picture a bit at different points. So that would be variants that you can imagine. You can work it out by yourself. You'll understand that from there. So let's go to the next slide. So to realize this kind of architecture, one of the standard fiber-based deployments that people have been doing in the past and would likely do in certain scenarios here in 5G is that they would deploy a ring fiber going from let's say DU all the way to all of its related RUs coming back to it. So kind of a ring topology at different sections would result in basically realization of what was shown in the previous slide. In the previous slide, what we had was shown as a logical link, but to realize that in practice, you would obviously need a physical medium to communicate. In a later slide that I will mention that have a solution at Astrome, which is related to a fiberless, purely based on wireless communication device, which can potentially replace these rings and bring back the multiple point-to-point scenario which was there in the previous slide. The thing to remember is that when you put a ring fiber, the capacity that the fiber needs to handle gets aggregated along all the units which are there. So in case of, let's say, a front haul loop that you see, each of the RU's capacity will have to be added together, and that will be the net capacity that the ring fiber will have to handle. So that's an important thing to remember. So the capacity is not as if there is one DU. You'll have to aggregate all of it and put it across in the fiber. For which the fiber, there are different technologies which is related to multi-mode and multiple. I think there are a few others which are bundling different kinds of fibers together. So it is realizable with certain caveats in place. Let's go to further slide. So what we talked about so far is a split where you have the core network and you have CU, DU, RU. The link between CU to DU and DU to RU have been standardized by different bodies. So IEEE has one standard called as 1914.1, which was released last year, which defines for both the links, the standards which are the NGFI1 and NGFI2. So those are the IEEE standards designations for the links between RU to DU and DU to CU respectively. And ECIPRI, which is basically from CPRI body, is basically definition which is valid between RU to DU. There is a lot of similarity between NGFI1 and ECIPRI, and ECIPRI has certain more variants which are related to splitting within the phi layer, which I was referring to previously. But overall, you can visualize it this way. EC3 is and NGFI1 is between RU and DU, and the other one, NGFI2 and F1 being a definition from 3GPP itself, is between DU to CU. Now, I have also mentioned some two other terms, HLS and LLS, that essentially stands for lower level split and higher level split. So the splits that we talked about, where we split one at option 2 and the other at option 7. So those are the two split boundaries which are referred to by LLS and HLS. If you look at 3GPP standards, you would come across these terms. So this would be helpful to realize, and then when you are reading the standard, you can remember these terms. This particular choice, where you have CU, DU, RU as physically different boxes, is suitable for certain applications where you need low latency and jitter. So there are certain applications which are related to ultra reliable low latency communication. So URLLC, this is a particular terminology which is being used, and also MMTC, which is massive machine type communication. All of these are basically communications which involve, let's say, an automated vehicle navigation, for instance, or let's say an industrial automation application where machines need to talk to other machines over the 5G network. So these are the applications where the link has to be very stable in terms of latency. So for such situations, this kind of split is the most recommended choice. Let's go to the next slide. The second type of choice is where you merge the DU and RU together. Now, this is a scenario that you would see primarily in case of massive MIMO. When you have a massive MIMO situation, the 5-layer feeds going to each and every antenna element, and basically the alignment of it has to be strongly maintained. And considering that, moving the entire 5-layer and parts of the essentially the entire 5-layer into the RU itself is beneficial for certain situations, especially when the array size is larger. So when you have massive MIMO base stations, this is a topology which is being discussed as the most preferred choice. Here the link between CU to DU plus RU remains the same as before, which is the NGFI2 or the F1. Okay, let's go further. As a choice number 3, you have possibility of using the core network and CU plus DU combined into one box and RU kept separate. And the link between RU and the combined box will be NGFI1 or the EC3 standard. Now, this possibility is something which is similar to the 4G's current scenario, where you have just the front haul and the back haul. So this is also called as a CRAN model, centralized RAN model, where it's closer to a cloud-based setup. I think this came up somewhere in 2011 or 12, this kind of architecture in the 4G itself. And if somebody wants to continue that kind of architecture for their network, so this is the closest resemblance for it. Let's go further. So, so far, whatever we talked about was basically the different aspects of the 5G as a standard and the motivation behind various design choices that 5G architecture has. So now I'll take maybe 5 to 10 minutes to explain the product GigaMesh, which is a unique one which at Astrome we have come up with. This we call as a wireless fiber. So this is literally a replacement for fiber, a wireless fiber, for the 5G applications and also which can stretch for rural broadband as well. Let's go further. Now, this is a first in the world multiple point-to-point radio in E-band that has been designed. E-band frequency is something like 71 to 76 and 81 to 86 gigahertz, which is way higher than the traditional band that 3G, 4G, and even 5G has been using or is going to use. This is a radio band which has been used mostly for backhaul in all of these networks. The way typically the E-band has been used and is being used currently is that you introduce a pair device, one on each of the ends on the towers, and establish a link between them using the E-band's wavelength. And on the other end, you just get an Ethernet link, which can be connected to any of the boxes. So it is like a replacement for the fiber line. If you were to lay, is being just replaced with two boxes. That is a traditional E-band point-to-point radio. Now, what we have done as GigaMesh is something unique. We have introduced an array antenna, which is even going up to a size of something like 400 elements, 400 element large size array, which can create multiple point-to-point links simultaneously. So in MIMO terminology, you would have come across something called as MU-MIMO, multi-user MIMO, where you do beamforming for each and every user. This has some resemblance to it, but it is somewhat different also from it. But it is that is the closest approximation that you can imagine, where we are creating multiple beams, but very narrow, going to something like 1-2 degrees each of them, and independently you can steer them electronically and also add and remove such beams. Now this is essentially a mechanism which you can imagine useful for different stages that we talked about. The link between CU to multiple DUs, or the link between multiple DU, a single DU to multiple RUs. So all of those are essentially multiple point-to-point scenarios, which in a traditional sense, you would look at replacing it as a ring fiber, which comes with its own disadvantages. So this architecture is very scalable, and with just a spectrum of at 250 megahertz, which is not much in case of 71 to 76 gigahertz, 5 gigahertz in itself, a very small slice of it, can give you 2 Gbps for each of the links. So that itself is realizable to give such a high capacity. And given the fact that unlike traditional point-to-point radio, the central section, let's say in case of CU to multiple DUs, the unit that is needed on the CU side will be only one, which can talk to multiple DU related units. Unlike the traditional point-to-point where you would need on the central side, let's say if you had to talk to 3 DUs, you would need at the central site 3 point-to-point devices, and then you would need one on each of the DUs. So that is not the scenario here. You would need only one at the center. The cost comes down dramatically with that. And it is modular enough, so it can scale to a large distance going up to 10 kilometers. So the array size that I was talking about of 400 elements gives a range of close to 10, even going up to 20 kilometers. Whereas smaller arrays of that can give comfortable links going up to a kilometer range, to 2 kilometer range. And this is very sort of a architectural fit for the 5G. Let's go to the next slide. So as a base unit, as I mentioned, this is operating in E-band frequencies, so which is like 71 to 76 and 81 to 86. And it can give you fiber-like capacities of like 12 Gbps, where we can form 6 links from one device. And the range is of the order of like 10 kilometers. And this is an ideal fit whether the network is 4G or 5G, or you just need it for rural broadband, where you have a fiber which you want to just extend it to different points, or you want to just do an enterprise connectivity. So that's essentially this is a solution, a wireless fiber-like solution for transport, a replacement for fiber. Let's go further. So this can be deployed in large distance scenarios like villages, and also it can be used for urban settings. So essentially, this is a mechanism to extend the range. So in urban settings, usually one of the key problems is right of way. So if you want to lay a new fiber, which is typically the case if you want to transport such a large data like the requirement of 5G, you need to dig trenches, which requires several permissions which are not easy to get. And so that essentially results in loss of business or loss of overall time, translating to a larger expense. So whereas in case of wireless, the deployment is quite simple. Anyway, you would spend effort to get the site, and you don't need to spend effort in getting the pathway of a fiber from two sites. So that's a big advantage that way for urban settings. In case of village, the advantage comes from the fact that you don't need to lay cables for larger distances or even maintain it. One of the standard problems, if you have come across in different deployments in villages and other places where, let's say, BharatNet and other projects have been deployed, is that there can be potential cable cuts because of illegal trench digging or any such cases. When that happens, the disruption is very significant and it doesn't come back so easily. So those kinds of issues are not there with wireless links, as well as there is no need to put that much effort to lay large distance cables for this. Let's go further. So on a summary note, basically this is a low-cost replacement for fiber, both in terms of CapEx as well as in terms of OpEx. OpEx because the links can be completely remotely controlled, so you can steer the beam the way you want just remotely. So any misalignments or installation related effort is all minimized. So the OpEx comes down dramatically there. And the deployment time is very fast because you just need to roughly place them and then the links align by themselves automatically, and very easy to maintain. Yes, let's go further. So essentially, this sort of summarizes various points and that I wanted to tell. I purposefully kept the presentation reasonably short so that I don't say dump too much information in a too short time on all of you. But I hope this gave you enough clarity of the way the 5G architecture is evolving, not just at the level of antenna, which is the MIMO section, but also as a network element with all different blocks coming in the path. If there are any specific questions or any queries, I'm open to know that. Yes. Maybe I'll just take a couple of more minutes and mention certain relevant standards and references that you can look at. One of the relevant standard, major standard that you should definitely look at is the 3GPP standard. The specific one, which is the most recent, is the release 16 stage 2. Stage 3 will come, I think, sometime mid next year, which will be the final of release 16. This is a completely open standard. You can download it. All of the related documents are available. The documents may take an effort to read, but it is worth reading. It is too, I would say, written in a very terse way. So it would take an effort to navigate it, but once you get used to it, you will be fine. If you have navigated, let's say, any standard related documents, bunch of them, then I think you'll be fine with this. And IEEE 1914.1 is another standard which came last year, 2019. So this standard is something which is available for purchase, and the link for that is given here. ECPRI standard, which is the other standard for communication between DU and RU, is an open standard. I have given the PDF link for it here. Another most, I would say, the first standard which came out from 5G sense is the ITU IMT 2020 standard, which is related to the specifications at top level. What should the 5G be? What are the things that the 5G needs to meet? So that is sort of an evaluation which started there, which then percolated down into the realization plan via the 3GPP and IEEE and the standard. Let's go further. So those are the relevant standards. I have also put some links of certain other talks, webinars, which you can go through, which will give you certain different perspectives on top of what I've told, and also certain other talks which are published as PDF. I've given as links, and there is one Medium article as well. So thank you. I would now welcome any questions that you would have.
Thank you, Dr. Prasad sir, for your informative talk on 5G evolution and your company's contribution towards building a product towards 5G applications. We had around almost 120 participants throughout the talk. So thank you very much for your informative talk. There are some couple of questions. So shall we go ahead?
Yes.
Yeah. The first question is, when transmitting at E-band, how is the atmospheric loss overcome for such a large range? Should the power transmitted be really high? That's the question.
Okay. So I'll go with that question. So the atmospheric loss when you go to higher frequency band is definitely higher. However, that comes with also another benefit. As you go to higher wavelengths, the directionality is more stronger. What does that mean? It means that with a smaller aperture in the antenna, you can achieve more narrower beam width. So with our device, for instance, we can achieve a 2-degree beam width to 1-degree beam width as two different variants, which is a very, very narrow beam width compared to, let's say, the beam width that you would have in, say, the 3G or the 5G's antenna, where you have something like sectoral sections of 10 degrees or 20 degrees as the beam width. So that is the kind of beam width change that this particular solution gives. The E-band makes that possible, and the technology that we have realizes that narrowness in the beam and compensates for the loss that is incurred. That's one thing. Second thing is that this is an infrastructure element. So the two ends of the device is not moving. So the beam forming that is being done here is very strong and very effective, and it is done from both sides. So beam forming is both on the transmit side as well as the receive side. So that gives basically much better link compensation. And as per our link margins that we have seen, we can easily do 20 kilometers. Hope that answers the question.
Thank you very much, sir. One more question is that regarding the range, it is mentioned that 10 kilometers is there between point-to-point communication. What about the buildings or hills in the path? How the deployability is there? Any limit on that?
Okay. I'm assuming this is all about for gigamesh.
Yeah, yes, sir.
So in case of gigamesh, which is again in E-band frequencies, much higher than the FR2 band of 5G. So the directionality is stronger, as I mentioned, which means that any obstruction in the pathway will break the link. So you would need line of sight for sure between the two devices. However, there are certain other scenarios that we have discovered as a possibility, which is in an urban setting. If there is let's say a surface, building surface, that building surface could be used as a reflector and create a reflected pathway in case of urban scenario, which can create a non-line of sight reflected link. So that is something which is a possibility in these bands. This you can visualize roughly as if that building is like a mirror, and we are just shining torch on that, and that is reflecting and then falling on the other side. So that's a possibility. It will introduce a small loss at that junction of transit, but it is a possibility. Another thing is that in case of natural obstructions, let's say there is a hilltop or something like that, a typical solution is to use a repeater on the hilltop, and then you can establish the link on the other side.
Okay, thank you, sir.
Can I
Next question is,
yes, sir.
yeah, please go ahead.
Prasad sir, so when you say that this is now operating as a wireless connection at E-band, so we just had the before talk was by Professor Anirudhan from IIT Madras. So he spoke about this how in rural we are trying to implement this 5G at 2.5 gigahertz basically, and he spoke about the various standards in India. So how will this E-band will get integrated with this whatever frequencies which we are working in India right now?
Right. See, the E-band frequency will be a separately licensed band. So, for instance, if you consider US, the licensing model there is something called as light license. Instead of an auction model where you have to pay revenue percentage for an operator, they need to buy the link for say some fixed fee. For instance, in US it is I think somewhere around $70-80 per link per year. Which is nothing compared to any of the auction bands. So that kind of cost is necessary to buy the link. Now, from a deployment scenario, as I mentioned in my talk, this is most suitable for infrastructure-oriented setup, which is like between CU to DUs or DU to RU. This does not come between RU to the end user. The end user being mobile telephony or any other infrastructure. So it does not come in that path. But basically, this is coming in the transport section of it. How do you transport the link or the data path to large distances? So or to distribute from one device to multiple other towers. So we come in those paths. So this is solving the transport problem, as you might have seen in some other terminology. This is the transport problem that this is solving. This is not solving the access problem. The access is the last part, which all of these standards define very carefully between the radio unit and the end user.
Okay, thank you for that answer.
Yeah. Sir, there's one more question. Will you be using intelligent surfaces? I don't know what is this question is about, but one of the parts.
Okay, that is a bit vague, but I will take the question for two possibilities. So one is that there are, I believe there are certain companies which have been doing metamaterial based antennas. I'm assuming that this question is related to that. Metamaterial based antennas essentially help in beam steering without using a electronic phase shifter. So this is a sort of a material property change which can be used for that. We are not planning to do that. So in fact, in our design, whatever we have developed in this product, this is not using metamaterial based phase shifters. We are rather doing something more fundamental, which will allow us to create multiple beams. If you use smart materials, you cannot create multiple beams. You can create only one beam. Whereas if you use some other techniques, which is what we have done, you can create multiple beings simultaneously.
Yeah. Thank you very much, sir. I think no. Yeah. I maybe, sir, because I also don't understand. Yeah. Thank you very much for answering all the questions. Kirti Priya madam will wind it up.
Yes, sir. Yeah.
Sir, there is one last question. I think somebody asked from academics. Will your device or your product can support us establishing a 5G lab in academics institutions? This is what is the question. Some participant has asked.
Certainly, let them get in touch with me. I believe the contact details are available. If not, you could share my email ID with that person. Not an issue there.
Yes, sir. Yes, sir. Yes, sir. We'll share your email ID. We'll share with the participant. Yeah. Thank you very much. Kirti Priya madam, we'll wind it up.
Yes, sir. Yeah.
I would like to also mention that yes, we are open to collaborations of that kind, as well as we are in the process of increasing our team strength also. So we are looking to expand. So we are looking out for good candidates.
Prasad sir, if you can turn on the video in your phone, maybe we can just take a picture.
Oh, I am not sure of the camera here. So I'm sorry, I think there's a problem here.
Okay. So then I think if it's not possible, then we can wind up the session. So thank you all the participants for staying with us through today's 2 talks. And tomorrow is the last day of the workshop. And tomorrow we have an interesting talk on measurements. Still now we are seeing all these network systems, circuits aspects. But finally, the OTA measurements is the talk is going to be given by Keysight. So the wireless application expert from KZ, Mr. Nazim Ahmad, is giving the talk tomorrow, and we start in the morning at 10:30 a.m. So please join us through the link tomorrow morning. So for today, we'll sign off from here. Thank you so much, Prasad sir, for accepting the invitation from our side. It was a pleasure to have you.
Thank you for organizing this. So this was very interesting for me also. Also interacting with all the participants. Thank you for giving me this opportunity to present. Thank you.
Thank you, sir.
Yeah. Thank you very much, sir. Thank you very much. Yeah, we'll close the session. Thank you.